with that flame. I'm going to go on to the node model. I want to talk about, so we've talked about the way that CCN views content. And it's a different view of content, right? It's the content itself, not its containers. And now I want to tie that to the moving parts, how the nodes work. For that, I've got to talk about what are the packets that it deals with. So we've got two kinds. There's an interest packet, which contains a name, and a little bit of other goop that I'll get into later, and a data packet, which is what you respond to an interest with. So an interest is asking a question. It's sort of like an HTTP GET. It's saying, does anybody have any data in this collection that matches this name? The data is an answer. And the data, because you have to secure the binding, includes the full name, the actual data, and the signature information, and then some other goop that I'll get into. And we encode this whole thing in binary in something that can be one-for-one transcoded to XML so that you can lump together multiple units of data, and you can extend any of those fields if you need to. In particular, you can add an arbitrary amount of security annotation. Now, I've been giving you names like that, like they were human-readable names. Those aren't CCN names, right? That's something that you're comfortable seeing, but a name in CCN is this opaque object, and the only thing that CCN cares is that it's a hierarchically structured object. Right? It uses the structure, but there's nothing else that it knows about. This is how a name is represented. It's a count of the number of components. It could be one if you want to use self-certifying flat names. I don't think you should, but you can. One component, that's fine. And then for each component, there's a count of the number of bytes in the component and that many bytes. So arbitrary binary data, we don't care. The only assumption is that there's hierarchy, and I'll tell you why in a second. If you want to encrypt your names so people can't see them, that's fine. If you want to put arbitrary binary data like the packet signature, the SHA-256, that's a real SHA-256. It's not an ASCII encoded version. Right? It's already taking a lot of bytes, and we don't want it to take any more. Why hierarchy? Well, it's just same reasons as IP. You want to do longest match lookups because they let you aggregate state. It means that as you get far away from places where the content might live, you don't have to know the details. You just have to know the place where there are more details. You get that by doing what in IP is called the longest match lookup. You find the longest prefix that matches the address that you've got. What we found with IP is that gives you log-n state scaling in the core. As the network grows, the state grows only as the logarithm. So even though we've got 3 billion hosts on the internet, we've got on the order of 300K roots in the core. And that's a completely tractable set of state, even for a global network. Now, this only applies to globally routable names, of course, just like some IP addresses are not globally routable. Net 10 addresses, 192.168, right? They don't even appear in the routing tables. And CCN has an equivalent of local names. Now, we're using longer names, right? They're often derived from human-readable names, and they've got maybe content identifiers on the end of them. And their variable lengths. First thought is, wow, it's going to cost a lot more to do the packet forwarding because packet lookups are going to be more expensive. Well, if you looked in the theoretical computer science conferences over the last decade, the progress in hashing has just been absolutely astounding. It really boggles the mind. There was a paper in the last talk from Martin Disfelbinger of University of Ilmenau and several colleagues, where he's computing collision-free hashes in linear time on 1 billion elements with the cost of about 6 microseconds per element, right? and 99% load factors in the hash table, right? So it's a hash table with 1 billion elements, collision-free, single probe will always get the right element, and all the space is used, no inefficiency. When I was growing up, that was impossible. You couldn't do that. Don Knuth said that you couldn't do that, right? You couldn't load it more than 30% and you would have collisions. But between Rasmus Page at University of Copenhagen and Martin, light years progress has been made in hashing. None of that can be used by IP, unfortunately. And that's because the structure of an IP address isn't explicit in the address. The way that you find out what is the net part and what is the host part of an IP address is by looking it up, because that information is kept in the routing table. And that means you can't hash the address to look it up. Or if you want to hash it, you hash it a bit at a time. So in an IPv4 address, you do 32 lookups, one for each prefix of the address. You can hash those, but that's a lot of lookups. Right? But you can't hash the address itself because you don't know what's the prefix. And the only way you can find out the prefix is by looking it up, which means that IP lookup structures, particularly for IP6, where you don't have the option of doing it a bit at a time, the lookup structures all tend to be either radix tree structures where you have to do a tree walk, and when you hit a terminal node of that tree, you found the longest match. So there, the routing table is telling you the address structure by terminating the walk, or that you can do in software, and you can do it fairly fast. It's log n cost, but it's still a tree walk, a lot of memory accesses. The other option is if you're doing it in hardware, you put in a TCAM, a ternary cam, which can do the match in parallel, but at a fabulous transistor budget. So DRAM is 1 transistor per cell. You make big memories out of it, gigabyte memories out of it. SRAM is 12 to 14 transistors per cell. It's really fast, so you can make the memories that sit right on the end of your serial to parallel converter for very high-speed links. But you pay an order of magnitude density cost. So for the same amount of dollars, you get a much smaller SRAM. TCAMs are 100 transistors per cell, right? Because you have to put the matching logic and priority logic in every cell. So it's 2 orders of magnitude more expensive, or 2 orders of magnitude less in density. You can't put very big routing tables in TCAM, or you spend a lot for the routers that use it, right? And this is a property of the way IP lookups work, the fact that the structure is implicit, not explicit. So badly wanted to fix that for CCN. CCN structure is explicit, which means that you can use hashing and all of this wonderful work over the last decade for lookups. And so even though the names are longer, you can look them up as fast as you can look up IP names, because the explicit structure enables a lot of recent research. Meaning. So we've got these names. What do they mean? Particularly the prefixes. Well, one of the big successes in IP was the routers don't, the names don't contain their meaning. The router has a set of rules for dealing with names. It does a longest match lookup to find them in a fib, in a forwarding information base. But the meaning of the name, where it goes, that's completely determined by the contents of the fib. And that's let us evolve a lot of different meanings. So it let us evolve this host addresses, the 127.1 address. Right? That didn't require any change to the IP forwarding model. What it caused is the way that you set up a fib is you never send 127.1 to anybody else. It's always you. And if you don't accept it locally, you drop it on the floor. And if you hear it from the outside world, you drop it on the floor. Local use addresses, net 10, 192.168, they're addresses that are deliberately not routable. If you try to push them across a boundary, the other side of that boundary refuses to accept them. They have different meaning in different networks, so you're free to give them local meaning. Some addresses have global meaning, net 18, net 13. They mean the same thing all over the world. That's defined by the way that you set up the routing table. So the semantics of addresses come from policy considerations in how you set up FIPS, how you can do the forwarding. It's the same for CCN. The node machinery doesn't give any meaning to addresses. In particular, addresses can have local meaning, which gets reused. And the one that I would really like to see in place, so that we didn't do this cable dance that we had to do this morning, was I have this presentation, which has a globally routable name. You could pick it up from anywhere in the world. In this room, there's a projector, and I can talk to that projector on a local name that's the same in every room. If a room has a projector, I can say this room / projector, and I'm talking to the projector. Right? So I could wire that into a piece of software that I never change. And when I want to do a presentation, I go to the projector and say, projector, here's a presentation. Put it up for me, please. Right? No wires to hook up. It's a name that rehooks itself up. It's a contextual name. And I can do lots of variations on that theme. It can be this room, it could be this meeting, it could be my family. Names that have useful local meaning that changes based on the context. And you want to make the name static and take advantage of the fact that it's being rebound. And particularly when you're doing more coupled worlds, you're doing energy management. So I would like to talk to this room's thermostat or this room's lights. If I want to do that with IP, what's the IP address of the light switch? Right? Who knows? How could I find out? There's just no way to express that. But in a content model, it's easy to give it a name. And if there's a communication infrastructure, it's easy to talk to that name. And particularly for lights, we're in the middle of a huge revolution in lighting. We're going from these very slow fluorescent and incandescent lights to LEDs. LEDs have the property that you can modulate them. You modulate them very fast, gigabits per second. If you're using them for lighting, you actually would like to modulate them, because the way the human visual system works is if the light's turning on and off faster than what's called the flicker fusion frequency, we perceive it at its brightest intensity. We don't see it turning on and off, and we don't see the average intensity, we see the brightest. That's just because the phosphors in our eye are fairly slow. So you save a lot of energy by modulating an LED light. Rather than just modulating it with a sine wave or some random frequency, why not put data on it? Why not have the room announcing what's in it? Why not have the photodiodes that we've got, the cameras in our laptop and the ambient light sensors in our phones? They could be reading the lights, finding out what's going on at the university. We're deploying all sorts of new local data-capable infrastructure. It's ideal for distributing content. Could give us a lot more awareness of the environment and could give us closed-loop coupling of the environment. It's not very amenable to an IP model, but it is very amenable to a content model. More rambling. Basic operation of CCN, so we talked about this before. If you want data, you broadcast, logically broadcast. You can do it over a point-to-point link, an IP tunnel, anything you want, but the basic mechanism is a dissemination, a broadcast model. You say what you're interested in, give the prefix of the data that you want. It's a collection of data, the stuff that matches that prefix, and anything that hears the interest can respond. If it has a data item, it can respond. So that's not the way Google works, that's the way that IP works. IP, you can't be interested in very much but packets that have your name in their destination address. But that's how IP works. When you put a node on a network, it does a broadcast called an ARP that says, this destination address, anybody interested in sending packets to this destination, send them to this MAC address. So it binds the logical identifier, your IP destination, to a physical identifier, some interface MAC. Routing can propagate that. They don't have to propagate the host part of the address, the entire address, because it can be covered by their prefix. So they need to know that binding to talk to on the local net, but they don't need to tell the rest of the world about it. And essentially, you're getting interest in the CCN nature of interest. We call them routes, but they flow out through the world, and packets follow those. That's a trail of breadcrumbs that cause your packets to be delivered. Here's a picture of that. So some host over here, 1234, it ARPs, it broadcasts, says, I'm at that IP address. It's got a couple of routers on the boundary. They look at the ARP, remember where that host is. They remember its MAC address so they can talk to it. But they're in charge of subnet 123, so they don't need to advertise the 1234 because the 123 identifies anything whose address starts with 123. So the 4 is redundant, it's irrelevant. So they just are propagating their prefix. Subnets get to the border. This network is telling its network identity, 1.2, right? So it doesn't have to propagate subnet level detail. So what we end up with is the 1.2 getting distributed via the whole internet. And now when anybody wants to send to that host, they send a 1.2, gets to the border router. It can look at the destination address and says, oh, it needs to go to subnet 123, so it sends to that subnet, and then the border routers know what the host is. Right? So we get fine-grained information close to the host, very coarse-grained information far away. That's what gave us the nice scaling. That's just how CCN works, no different. Transport level. So here's something fairly exotic. You sent out this interest. There's some matching data. The matching data coming back, it makes the interest go away. So the data follows the interest. You can view as the interest is flowing out, it's laying down breadcrumbs. That's just like IP routes. But we have the model that as data is coming back, it consumes the route. It eats the breadcrumb so that other data items can't follow it. You'd need to express a new interest in order to get additional data items. If you want a lot of data in progress, if you've got a big bandwidth delay product that you need to fill, you can express several interests in parallel for different data, and you'll get all of that data simultaneously. And that's similar to a TCP window. In fact, this whole mechanism is really similar to a TCP window. If you look at how a TCP conversation is working, the sender sends until it fills the window. The window tells it how much it can inject into the network, and then it stops. And it's got to wait for an ACK before it can send new data. Generally, you get an ACK in for a packet, and the sender that allows the sender to send a new packet. It exposes another chunk of space. And so you have a sender that's turning ACKs into data packets, and it basically consumes the ACK. And symmetric thing is happening on the receiver. It turns data packets into ACKs. That essentially consumes the data packet. They're working in a pairing, in a flow balance. If you've got this pairing, if you've got this balance, then there's a beautiful piece of work by Frank Kelly of Cambridge, a book he published in '79, which I didn't read it until '89, and would have saved me a lot of time if I'd gotten to it a decade earlier, called Reversibility in Stochastic Networks, where he talks about the properties of this detail balance. And the first principles properties are, if you construct a network that's got flow balance, or even approximate flow balance, some affine transform of a balance, then it's absolutely robust. It's Lyapunov stable under arbitrary traffic and arbitrary load, which is basically, it's why we could grow the internet. It doesn't matter how big you make it, doesn't matter how many hosts you put on it. The balance property lets all of the interested parties control the traffic so that it can not get very far out of balance. So there's a bound on how bad it can get. Now, that bound can still be pretty bad. It's the amount of buffering that we've got in the network, and we tend to put a lot of buffering in the network. And so things can suck pretty badly while you're waiting for all those packets to go through. But it's a bound, and it's a hard bound, hard mathematical bound, that says you can grow this network. So it's a really important property, and this is another one of those things that should be taught, isn't taught. If you're designing protocols, you want to think really hard about the flow balance and the symmetry properties that it implies. TCP's used it to great effect. CCN's using it for the same reasons. And TCP uses it in a unicast scenario because it's point-to-point conversation. But the nice thing about reading Frank's work is it works at the traffic level. It's, can you pair a packet with another packet? We pair interests in data. And they're broadcast. Both of them could be broadcast. full multicast scenarios, replication scenarios, it's still stable. We struggled for decades trying to make multicast versions of TCP and failed. It's really hard to make multicast transport protocols. And part of that is not understanding the underlying dynamics and the balances that you have to maintain. Well, you can show that balance for CCN formally. We haven't done the work to show it in simulation. We've done it at small scale in our prototype implementation, but it maintains it. It works. What Frank said works. So I said I was going to talk about the machinery. Here's the machinery. Start with the IP machinery. So this is just straight out of 791, right? You read the RFC. This is the picture it gives you. You've got interfaces that are point-to-point wires. You've got some network core. It's got a table in it called the FIB, which is the forwarding information base. It tells it for a given destination address where you should send the packet. And these interfaces, because you're stat muxing, the interfaces have to have a buffer in front of them. That's right, because there is no global scheduling system that prevents packet conflicts. It's perfectly reasonable to have a packet arrive on interface 0 and 1 simultaneously bound for interface 2. Right? So even if all the wires are the same speed, you're going to instantaneously overload the output interface by a factor of 2. And there's no requirement that those interfaces be the same speed. Very often, if some are local interfaces and some are long haul, the locals tend to be many orders of magnitude fatter, higher bandwidth than the long haul interface because of the economics of bandwidth. So you're required by the design of the protocol to have a buffer to handle the transient overloads and the rate adaptation. And the packet forwarding model is packet comes off the wire. First thing you have to check is its destination address me? Is it bound for this node? If so, you punt it up to your transport stack. If not, you've got to prevent loops in IP because it's not aware of the data. The data is opaque. So every packet has a time to live, which is basically a loop killer. You decrement it at every hop. So you check the time to live. If it's not you, you're going to forward it, but you're not going to forward it if it's off its time to live. Check it. If it's non-zero, you decrement it, and you can forward it. The way that you forward it is look up its destination address in the FIB, do a longest match lookup. The FIB contains an outgoing interface, and you put it on the queue for that interface. And that's the packet processing. And that FIB can be exactly one outgoing interface. In IP, you have to forward on a tree, this gravity property. You have to do loop-free forwarding, because if you had loops, it would kill the network. And that means, in the way that we normally architect it, is no matter how rich the network graph is, we overlay a spanning tree on it, and we forward via that spanning tree. And the tree has the property that there's one path between any two nodes. It means there's only ever one outgoing interface in the FIB. Here's the CCN node model. It's got more stuff in it. So our interfaces are broadcast. They're not wires. Abstractly, they're radios, right? You can broadcast an interest on them. They can be point-to-point links. They can be tunnels over IP to any point in the world. We don't care. And they can be applications. CCN, there's no difference between demuxing to a local app and demuxing to some foreign agent. It's demuxing. And so there isn't an is it me decision, right? That's just demuxing to a local app. And you need that if you're doing multipoint protocols, because you may have a service agent locally, but the data may be available multiple places, and so you want to ask the local copy, but you want to ask others. So whenever you've got a protocol where you can fan data out or fan data in, then if you do the classical layer 3, layer 4 split, you end up hosing yourself because you have to either send the data up or out. And if you want to send it both ways, you can't do it. That's not how your protocol stack is organized. So when you do many-to-many broadcast communication, you need to put applications in the same framework that you put everything else in. And that simplifies stuff. 3 different data structures. One we call the content store. That's where you remember data that you've seen before. And you view it as the buffer memory. In fact, it is the buffer memory in a normal router. Same memory, it's got a different replacement property. You do LRU rather than MRU replacement. You don't treat it as a FIFO. But it remembers the packets that you've got. You can verify all of those packets, so you can get rid of corrupt ones. And there's an index structure that lets you go from the name into that content store. So I said that when you send an interest, it lays down breadcrumbs, and then data follows those breadcrumbs back, and it consumes them in the process. Well, that's embodied in this pending interest table. So that's an interest that you couldn't satisfy and you sent on to somebody else, but you have to remember it. So if they give you data, you can give that data to the people who originally asked you. Right? So it's got the name from the interest and the face that the interest arrived on. And so when data arrives, that's the face the data is going to go out. So that's the breadcrumb. And for every interest that you can't satisfy locally, but you forward remotely, there's going to be an entry there. Then lastly, there's a fib. Looks just like an IP fib. But rather than having a single outgoing interface, it's got a list. And that's because in CCN, data can live multiple places. And so what you put in your fib is all the places where the data might be. In IP, it's a different semantic. The interface, output interface is where the data must be. When you announce a prefix, the contract that your routing protocol is making with the network is everything covered by that prefix is reachable via me. And that has to be the contract, because the people that you're telling the prefix can only send the data one place. Right? And so if they send you a datagram with an address in it, you damn well better be able to handle that datagram. Right? You have to get it closer to the destination, because they only had one choice and you were the choice. Right? So you get global dependencies in IP routing because you have to put on a spanning tree where you have to be able to handle all the traffic covered by a prefix. There's no such global dependency in content routing. Right? If there are 3 places that the content might be, then CCN is perfectly capable of asking all 3. It can ask all 3 simultaneously, and 2 may not have it. Only one needs to answer. So you don't have global dependencies, you just get local dependencies. You get a much weaker contract. You have these 3 tables, you still only do one lookup. An interest comes in, you have a single index structure, you look up the interest, I got a picture, doesn't show very much, but I'll at least put it in. An interest arrive. We're looking at a state where something on that wireless network is trying to pull down a video, right, which has got that name, part.com videos, widget.a.mpeg. And it's version 3 of the video. And you can see up here, we got block 0, the first block of the video, and it's in the content store. And block 1 has been requested, it's in the pit, but no data has come back yet, so it's still pending. And the thing that's asking for the video is asking for the next block, so it's asking for block 2, the 3rd block of the video. That interest arrive. We take the name there, we look it up in our index structure, longest match lookup. It doesn't match anything in the content store because there's no S2, and it doesn't match anything in the pit. Again, there's no S2, there's an S1. Longest match lookup, it does match the park.com and the fib. So we don't have the data the application's interested in, but the fib says we might know where to get it. And so we'll forward the interest. The way that we forward the interest is we take the face list out of the fib. The question arrived on face 0, and you never send a question back out the face that it came in on. You know, that's flooding semantics. That would be stupid. It's just going to loop. So if you're going to forward it, you remove the face that it arrived on, which is 0, and you send it out face 1, presumably to some server at Park. So that's going to bubble it upstream. And you make an entry in the PIT that said, I'm asking for park.com widgets mpeg /s2, right? So it says that I've got a second pending interest, one that's being propagated. Packet came in, it's a single lookup, right? It can be 3 different places, but they have a priority order. If you've already got matching content, you always want to return it. So if you get a content store match, you satisfy the interest, you send that data out the wire, and you're done. Throw away the interest. If you get a PIT match, then either this is a new interest in the same data, so somebody on a different face is asking for data that you're already trying to get. If that's happening, then you simply add that new face to the PIT entry and say, okay, I'm getting it, and when it comes in, you'll get a copy as well as the guy who asked the first time. Right? So that requesting faces, that's another list. Right? And if you get a new PIT entry for data you've already requested, you add it to that list, and now you throw away the request because you've remembered what you need to remember. If it's a duplicate, or if it's coming in on the same face, it's a guy that's impatient and he's asking you again, or somebody who didn't hear the first request and is asking again. And when the data comes in, you're going to satisfy their interest, so you throw away the interest. You don't need to do anything. Right? So there's a priority. Look it up in the content store. If it's not there, look it up in the PIT. If it's not there, look it up in the fib. One lookup where you order the entries in the lookup so that you get the entries in priority order. Right? And that's easy to do with a particular kind of hash table called a creep, and a treep, a priority tree. And there's probably other structures that do it as fast, but it's hash, it's an order 1 lookup. So 1 lookup, same cost as IP, more data structures. When data packet arrives, so we sent the interest out that interface, data packet comes back in. We look up data packets only in the PIT. Well, that's not strictly true. Look up the data packet. If it's in the content store, it's a duplicate and you throw it away. Right? And the data is idempotent. Right? Looking up a data packet means up to and including the data itself. Right? So if you find it in the content store, you've got it unambiguously. Right? Up to the SHA-256 checksum, you've really got this data packet. And so you don't need the duplicate copy because you know it's a duplicate. And you toss it. What that means is content can't loop in CCN. Right? If data goes around a loop for any reason, as soon as it gets to a place where it's already been, you look it up in the content store, you say, I've got that, and you throw the copy away. Right? So you suppress duplicates at the content level because it's a content protocol. That means that you can use this simple diffusion flooding paradigm because the data is recorded. So we look up the packet. If we find it in the content store, it's a duplicate, we discard it. If we find it in the PIT, it's something that we asked for. What was this one? This was S1, so I do find that in the PIT. So somebody asked for this. What that means is I record the packet in my content store. I got something that was asked for, it's relevant data. And then for each interface that's listed in the PIT, I send the packet out that interface. So what that is, I add something to the work list of the outgoing interface that says, ship this packet that's now in the content store. And I say it that way because in CCN there aren't queues. Conceptually, the model is a router, an upstream node, always satisfies requests from its content store. What you're asking for is something that's in the upstream's content store. If it doesn't have something in its content store, but it knows a way to get it, then recursively it will ask its upstream for that stuff, put it in the content store, and then send it to you. But you're always satisfying requests out of a memory. The memory in CCN is explicit rather than being an implicit buffer memory in IP. And because of that, you don't need queues on any of the interfaces because you don't have to do rate matching. They get the data when they want to get the data out of a random access memory, and they get it in the order that they want to get it. So the service policy is not the sequential policy that's motivated by queues, but it's an instantaneous policy per face that says, okay, what data do I need to send now based on the downstream demands on me in the downstream contract? So you don't have the ordering implications. You don't, roughly 50% of the QoS problems that we see on the internet are artifacts of queues. The fact that a queue introduces this big delay and it's serial. You can put stuff on the end of a queue. You can't put it on the middle. You can't service out of the middle. If you get rid of queues, then you get rid of that 50%, because the service policy can use the fact that you're servicing out of a RAM. And it can be much more responsive to the downstream demands and to the instantaneous changes in those demands. So we've gone through the node behavior. Let's do a side-by-side. So what I've just been saying, these are the same parts that are in an IP router. They're just combined in slightly different ways. The buffer memory turns into the content store. Same memory, same amount of memory. All you're doing is changing the replacement policy. Goodness is not in a queue, in a FIFO buffer, you want to keep it empty all the time because it's a shock absorber. And if it's not empty, it can't do its job. So you forget what's in the queue as quickly as you can. And that's good for the TCP protocols because once you've sent that data, it's of no further value to you. But given the relative costs of bandwidth and memory, actually the stuff in that memory is really valuable and you don't want to spend bandwidth to refill it. So the model in CCN is, no, if you've got it, remember it and use it again so you don't have to spend more bandwidth to get another copy. If you've already got a copy, great. So once data's arrived, you hang on to it for as long as possible. So that's a different replacement property on the memory. It's still memory, but you're going to an LRU replacement rather than try to forget as soon as possible. But it is the packet buffers, right? You post a buffer to a face, the face fills it with the bits that arrive. Then you look up its name in this index structure, and if you want to remember it, right, it's a data packet that arrived that satisfies from some interest. What you put, the way that you put it in the content memory is you put a pointer to that packet, the one where the bits landed, right? They came off the wire, they landed in some chunk of memory. You put a pointer to that memory in the index structure. You don't copy anything. This content memory isn't like some database, right? It's where your packets live. And so you're not moving stuff around, you're just remembering them in this index. The really new thing in CCN, that's not in an IP router, is an index structure, and that's so that you can reuse stuff. What's next? Fibs, basically identical, except CCN doesn't need to forward on trees. So you can have lists of interfaces rather than a single interface. Transport, because you're doing multipoint, a lot of the transport state turns into the PIT. And it's because the data could need to be replicated. So the same reason that when Cisco did PGM, their multicast transport, they had to stick part of it into the routers is because the data needed to be replicated. It's the same problem. You need to be aware of the local connectivity in order to duplicate data. And so a lot of the layer 4 stuff, it doesn't make sense. It has to move down. There isn't a me test for the same reason. If you're doing multipoint, me just has to be completely symmetric, the same as any other interface. And so you forward to apps the way you forward to anything else. You never modify data. There's no TTL check. Nothing can loop, so there'd be no reason to do it. And we don't want to modify packets because it means that we can't assess their integrity. But that means that if you're doing particularly a silicon pipeline, you can do it a lot faster because a lot of an IP forwarding ASIC, a lot of its real estate is involved in the implications of the TTL update. You have to rewrite the packet. So that really changes the flow through semantics. And it's not just the TTL, because when you change it, you have to also change the checksum. So there's some computation and several fields that have to be updated. None of that happens in CCN.